So now I'm going to do a little more complicated circuit. Okay. It doesn't look that much complicated when we start, but you're going to see here sort of how this plays out. So let's imagine that we've got a power supply right here. Okay. And we have a capacitor C1, and we have a switch, and the switch can be position A, or the switch can go to position B. And then we have another capacitor C2. So when the switch is in position A, then what happens is this is one circuit and capacitor 2 is not connected. When the switch is moved to position B, this is a circuit right there, but the battery is not connected. So this switch allows us to go back and forth here between two different things. So let's say that V0 here is going to be 7.75 volts. Let's say that C1 is going to be 4.67 microfarads. And let's say that C2 is 6.35 microfarads. And I'm going to start with the assumption that the capacitors are uncharged, so Q1 naught equals Q2 naught equals 0. And I'm going to assume the switch is going straight up. It's not connected to A and it's not connected to B, so it is neutral. So the first step is I want to throw the switch into position A. So now what we have is we have a circuit that looks like this. And I want to know what is the voltage and the charge on each of the capacitors. Okay. Well, this actually turns out not to be that hard. Okay. Because right away we see that capacitor 2 is not even connected. If capacitor 2 is not connected, V2 is 0 and Q2 is 0. Done. We got half of the question done right now. Okay, now for capacitor 1, it's connected to the volt. So this is all one voltage. This is all one voltage. If that difference right there is 7.75 volts, that's going to be 7.75 volts. So that means that V1 is 7.75 volts. Okay, we know that Q is CV. So Q1 is going to be C1 V0. If you multiply that out, then that's going to give you 3.62 times 10 to the minus 5th coulombs. Okay, so now we have this right here. Okay, we answered the question. Do not forget on a test, because students frequently forget on a test, that I asked for all the charges and voltages, and that includes capacitor 2, which is not connected. It still exists in the universe, and so you still want to give that parameter right there. Because if it's not that, if that's not what you get, if you measure it, then something else is going wrong in your circuit. Now, switch to neutral. So now we have this. Okay. Well, C2 still is not, had never been connected, so that means that it still has 0 voltage and 0 charge. But when I disconnected the switch and put it into neutral, there was already charge on that capacitor. There's nowhere for the charge to go. The charge can't go anywhere, so the charge is still there. So Q1 did not change. Q1 is still 3.62 times 10 to the minus 5th coulombs, and therefore V1 is still 7.75 volts. Because if you've got charge on the capacitor, you've got a voltage. Okay, so nothing changed. Now, and the switch is to position B. Now what happens is we have all this charge here, okay, and some of it goes over there. Okay. So now we've redistributed the charge. So I want to know what's the voltage and what is the charge in each one. Well, obviously Q1 changed, Q2 changed, but the voltage is Q over C. So that means this voltage did not, so V1 is not going to stay the same. It's going to change because some of the charge left. If the charge decreased because some of it went to the other capacitor, that means V1 is going to end up being less than the original. Okay, so there's going to be a change here. So what's our takeaway here? Well, we have these two capacitors, C1, C2, and they are effectively connected like that. Okay, so the tops are connected together, the bottoms, they're parallel. So this acts like one capacitor right here, some equivalent capacitance. Well, that's going to be C1 plus C2. So the equivalent capacitance is going to be equal to, when you add the two together, 11.02 microcoulombs. Well, we know that voltage is going to be Q over C. So what's the total charge? We got Q1 and Q2, they're in parallel. So Q1 plus Q2 is the total charge. So the total charge, wait a minute, where did the charge originally come from? All the charge originally was only on C1. And then some of it went over here, but the total charge stays the same. That total charge was the charge that was originally on C1. So that's going to be the 3.2 times 10 to the minus 5th coulombs. So 3.62 times 10 to the minus 5th coulombs divided by the 11.02 times 10 to the minus 6. Sorry, that's microfarads, not microcoulombs. Microfarads. Okay, so the voltage is going to be 3.28 volts. Okay, now I know there's a 7.75 volt battery over there, and that charged up C1 to 7.75 volts, but when you switched the switch to position B, some of the charge went away. When the charge went away, it took away some of the energy. Therefore, the voltage dropped on C1. Okay, so we can say that V1 equals V2 equals 3.28 volts because we know that they are in parallel, so they have to be the same. What about charge? Well, Q equals CV. So Q1 is going to be the 4.67 times 10 to the minus 6 farads times 3.28 volts. So Q1 has now dropped to 1.53 times 10 to the minus 5th coulombs. Q2 is going to be 6.35 times 10 to the minus 6 farads times 3.28 volts. So Q2 is no longer 0. It's going to be 2.08 times 10 to the minus 5th coulombs. Now, what is Q1 plus Q2? That's going to be 3.61 times 10 to the minus 5th coulombs. And that is within rounding error of the 3.62 that we expected it to be. So that means that we probably did this correct. Okay. Now, switch to neutral. So now switch is back in the neutral position. C1, C2. Well, now we have charge here. It's got nowhere to go. Now this charge has nowhere to go. So that means nothing changes. So when you switch to neutral, then V1 is still equal to V2, which is 3.28 volts. Q1 is still 1.53 times 10 to the minus 5th coulombs, and Q2 is still 2.08 times 10 to the minus 5th coulombs. There's nowhere for anything to go. Switch to A. So now we're back here. Well, now, V1 is now back to the original because this is connected back up again. So V1 is now 7.75 volts. Q1 is now going to get back to 3.62 times 10 to the minus 5th coulomb because more charge is going to flow in order to balance it back up to the right voltage. What about C2? C2 is not connected. Now, before it was 0, but we left it with charge on it in this problem. So that means it still has charge on it. So that means that Q2 is still going to be 2.08 times 10 to the minus 5th coulombs, which means there's still a V2. And V2 is still going to be equal to 3.28 volts. Now, let's switch back to B. So now we switch back to B. Now, what's going to happen now? Well, we had all this charge here. We had some charge here, so some of this charge is now going to move over here. Okay, and so now it's going to rearrange itself again. So what happens? How does this rearrange itself? Well, we look at it, we say, well, gosh, it's still the same equivalent capacitor of 11.2 microfarads. The Q total is going to be equal to the charge that was on Q1, 3.62 times 10 to the minus coulombs, plus the leftover charge that was still sitting on the other capacitor, C2, so that gives us 5.70 times 10 to the minus 5th coulombs. Well, that means the total voltage, V1, the voltage on the equivalent capacitor, voltage is going to be equal to Q over C, so that's going to be equal to 5.7 times 10 to the minus 5th coulombs divided by the 11.02 times 10 to the minus 6 farads, and that comes out to be 5.17 volts. So V1 equals V2 equals 5.17 volts. But we know that Q1 is now going to be that V times C1 times V. So that turns out to be equal to now 2.41 times 10 to the minus 5th coulombs. Q2 is going to be C2V, and so that's going to be now equal to 3.28 times 10 to the minus 5th coulombs. So now we've pumped up the charge a little bit. We've pumped up the voltage. Now, if I keep doing this, go back over here, this keeps the same charge. I recharge capacitor 1, I go back to position C, and then I distribute the charge again. So I keep throwing the switch back and forth, back and forth, back and forth, and what will happen is these two capacitors will asymptotically approach V0, and the charges will eventually asymptotically approach the final.